Thank you all for switching to the presentation of Ludo. Ludo Cornelissen is one of the postdocs that worked on the DAME project. After a couple of years into the project, he decided to shift his working career to one of our partners. So he went to work at Intel. And today he will talk about his work that he did for the DAME project on the automated pneumothorax detection and localization on chest X-ray images using a deeply supervised UNet. So Ludo, the screen is yours.
Thanks, and good afternoon, everyone. So after what I think was a very nice introduction into this field by 𝐃𝐀𝐌𝐄, I will take a slightly different route, showing you more the actual technical contents of such a development process for a deep learning algorithm. And this particular project was carried out for the DAME project, and it's a collaboration with the Department of Trauma Surgery. And why that is, I'll get to that in a minute. I think, one of the slides I always like to show first is it's about the promise of AI in medicine. Like, why would you want to use it in the first place? And of course, the video we saw in the lobby earlier also answers partially that question. But I like this quote because it says, like, the wisdom contained in the decisions by nearly all clinicians and the outcomes of billions of patients should inform the care of each patient. So to me, that's a really fundamental aspect of why you would want to use AI, because it just can, almost by definition, can process and use information on much larger scale than what a human doctor could do. To immediately look at the other side of things, it's maybe good to realize that it has been around for a while. For instance, there's this other nice quote, which looks like basically says that okay, we're getting pretty close to actually using AI effectively, or it's recognized there are some issues, but it's a pretty optimistic quote, and this is actually from 1993. So back then they were also already thinking about this, even though at that time it was far less well developed than it currently is. So I think this is interesting to see. Okay, so let's go on to the problem at hand. This project was about pneumothorax detection. Pneumothorax is essentially a collapsed lung. And in this case, we were looking particularly at pneumothorax in trauma cases. In approximately 15% of thorax trauma cases, pneumothorax will occur. And then it has to be treated pretty much immediately to prevent it from developing into a tension pneumothorax or worse. And often in these trauma cases, the diagnosis is made on using an X-ray, a chest X-ray, but CT is the actual gold standard. And it can be very hard to spot pneumothoraxes on X-rays, as we'll also see later on during my talk. And then there are different types of pneumothorax, or lateral or ventral, and one is easier to spot than the other. And actually, the question that we kind of set out from for this is pretty typical for a medical AI project. I mean, how do we make the most out of the limited data that we have available? Because this quote about billions of patients, it's all very nice, but in practice you don't have that. Of course, you don't have a data set with billions of patients available. Oh. I'm trying to go to the next slide, but my right. Okay, sorry for that. I hope it now transitioned for all of you. So about this data problem, the way we thought about it was, well, usually when people try to make a pneumothorax detector, they would use global labels. So that essentially means, you show the system an X-ray and you say, hey, there is a pneumothorax in this image. But we went for, well, a little bit different approach, where we say, okay, the green part is healthy lung tissue, and the red part is actually afflicted, or, well, in the pneumothorax case, means there is no lung tissue there. There's air there, which shouldn't be there. And those areas we marked with in red. And then that means you go to a local representation. So instead, you're essentially saying, hey, look, here is the pneumothorax in this image. And as you can understand, this might provide a neural network with much stronger information about the image that it can learn from. Of course, it also takes extra effort, right? You have to annotate all these afflicted lung segments manually. Now, I'm trying to go to the next slide again for another example of this. I don't know if it has worked for you, but for me, it's showing me a loading circle. Of course, this was working perfectly when I tested it before, but okay, well, so here you see another example. You have these pneumothorax here in the top and bottom of the lung. So, I see that the audience sees it right away. That's good. Let's move then to what is probably the most important part of a deep learning project, in my view at least, which is the data set. So for our project, we looked at trauma patients seen in the UMCG over a period of 10 years, which were older than 16, and which, of course, had a chest X-ray available. I should say it is standard protocol to make that. So all patients should have it, ideally, but yeah, as we will see in practice, that might be a bit different. And ideally, we would also like to have a thorax CT available to have the true gold standard. So when we search for those criteria, starting out, we got close to 3,000 patients to start out with, and then we started excluding because for various reasons, maybe the patient would not have a CR available, maybe it was not available in the system anymore, maybe a report was unretrievable. So as we went along on this project, a lot of these technical issues started creeping up. And in the end, we split the group into patients with a CT thorax and without. And to kind of balance the data set, we wanted to have at least have about half the patients. We would be absolutely sure that we were using the proper gold standard, and the other half is don't have the CT available. The reason for doing this is that, yeah, if we were to use only the CT patients with a CT, we would end up with a very small data set. That's not ideal. So in the end, we got about 800 patients with about 1,000 chest radiograph images. And then, well, equally important as gathering your data set, also describing it, I think. So we looked at the age distribution of our patients. These are kind of typical for trauma patients. You see also a lot of, or relatively high number of younger patients, motorcycle accident, those kind of things. And one other thing that we were very wary of is that we really only wanted to use the photo, the X-ray on which the diagnosis was based. So typically this is the first X-ray taken for these patients. And then when a pneumothorax is treated, a drain is placed in the lungs. And yeah, then of course, any follow-up X-rays might be to assess whether the pneumothorax was treated successfully, whether the drain worked, whether it could relieve the air through the drain. But yeah, then of course you would have that drain there, and that is a significant confounder when you're thinking about pneumothorax detection. any image that has a drain, well, yeah, kind of logically follows that there must be or has been a pneumothorax there. So we really try to exclude those follow-up images as much as possible, automatically though. So we filtered as much as we could from the data we got from the PACS, the picture archiving communication system of the hospital. We tried to make this first in the right graph, the number of chest radiographs per patient, try to push that number of patients that had only one radiograph as high as possible. Some cases were very hard to filter because the timestamps were a bit messed up or other technical difficulties. But yeah, in the end, I think we managed to do quite well. And then along the way, we encountered another confounder, possible confounder in the data set, which is the presence of rib fractures. So if your ribs are broken, you can imagine the lungs are more likely to get punctured and a pneumothorax is more likely to develop. So those indicate an elevated risk of pneumothorax. And you see this back in the data. So in the pie chart here, you see that the majority of cases were normal. There were about 8% of patients who had only a pneumothorax, 13% who had only rib fractures, but 23% who had both. And actually, there's a nice way to kind of handle this. You just have to make sure that you divide your data set in such a way that all categories are represented equally in your test, train, and validation data sets. So here you see, I hope everyone is aware of, or is familiar with these concepts. Typically, you would train on your training data set, then during training, check whether the performance is okay on your validation set, and only after the whole process, you report the performance on the test set. And then, of course, it's important that these sets are representative of the true data distribution. So here you see how we divided our images over these three test, train, and validation sets. And then, there was yet another confounder coming up. I mentioned this in the beginning, but actually up to 40% of these pneumothorax cases were not detected straight away on the chest radiograph, but they were only caught later on the CT thorax. And this is a much bigger problem essentially. And there's not a really clear way how you can handle this. But what we did was, we say, okay, we're not only going to annotate the pneumothorax, we're also going to look at indirect signs. And indirect signs can be subcutaneous emphysema or a deep sulcus sign. And we're also going to annotate those. Now, this is going to be, now it's lagging for me again, but I hope you can see it already. So the blue areas on this image, those are areas of subcutaneous emphysema. So they show, if you see that on an X-ray, then that's an indirect sign that there might be a pneumothorax present there. Oh, now it's, I think I accidentally, this is the slide you should have seen, I hope. Okay, and then getting to the actual model part. So how do we now made these annotations. We made them using the NOOS platform, which was developed by 𝐃𝐀𝐿𝐿, one of the partners in the project. And with the NOOS platform, you can draw these segmentation maps really quickly and also already train a model as you're annotating along the way. But the model we got from NOOS was not quite satisfactory for this task. So we had to take it one step deeper, essentially. So what we did, we used an approach called segmentation-assisted classification, and it works roughly like this. So we start with an X-ray image, we feed it to a classification model. In our case, we used EfficientNet, And then you get a classification output. That's the global label. So is there pneumothorax, yes or no? And then we attach the UNet on top of that using particular layers in the classification network and feeding them into the UNet. And this is a typical segmentation network. And then you will get the segmentation output from that. So that provides the localization. And yeah, when you do that, you can then combine the losses of these two models in a weighted way. And you can play with the parameters a bit. And then actually you can make a pretty good classifier. And now I should say, we were lucky that there was also a public data set on this problem available. So a paper came out in 2019 by Google, which released their test set for this problem and labels on these test sets. So they used global labels only, but that was okay. These are the results that they reported. So very good classification performance, AUC of 96% almost. And actually, when we tried then so their AUC was 94, and when we used our model on their data on their test set, we found that we got an AUC of 96 performance, so even slightly better than theirs actually. So that was a kind of a hint that this model that provided us confidence that this approach works. But when we used our model on our own data set, it turned out that the AUC dropped dramatically. So here I hope you can see it. The blue graph is the curve for the UMCG data set, and it's really quite dramatic. Then, of course, there are tricks to counter this. You can retrain the model on the UMCG data set, which is what we did. It improved a bit. We got up to 91% of AUC. But yeah, still, I think this first graph on the left here, where you see a very good performance on chest X-ray 14, but very poor performance on the UMCG dataset. That really illustrates the problem in my mind. That yeah, these models are so dataset specific, so you have to validate them before using them on your own data. And I think the reason here is that chest X-ray 14 is quite a different patient population. So those include also ICU patients, much more general than just trauma patients. Yeah, in view of time, I go through this quickly. So here you see examples of the output of our model on the test set. So you see on the left is the bare image, in the middle the annotations, and on the right the model predictions for both the indirect and the direct pneumothorax. So to wrap it up, we were able to detect pneumothoraxes with a decent AUC. It's not as good as we would like it to be, but it's getting there. And this approach of merging global and local labels together can provide you with localization and therefore also with explainability of the model. A doctor is much more likely to trust a model if it can provide these kind of maps of where indirect and direct signs for the pathology are located. But I think the most important bottom line is, yeah, the general patient population does not necessarily work for trauma patients. So you really have to do either fine-tuning or at least validation. And I know that pneumothorax detection algorithms are finding their way into actual X-ray, commercial X-ray machines. For instance, I know that Intel has been working with one partner to actually have such an algorithm deployed. But yeah, I think that still validation on local data will be necessary, and that some kind of QA process, as we have for CT and MR machines as well, is also necessary for algorithms. And with that, I think I'm a little bit over time. I'd like to thank my collaborators in this. My slide is not showing again. This is annoying. Anyway, main contributors, Vincent Steerler, Eelco Venema, Frank Eijkma, from trauma department, my students, Bernardo, Prajakta, Stavroula and Bendix, and of course everyone else involved as well. Thank you very much.
Okay, thank you, Ludo, for the nice presentation of this outcome of the DANE project. Are there any questions from the audience? We can do some quick questions because we are now into the break. So there's a question from Johannes. Do you think that there are other differences between the two data sets apart from the patient type? Often enough, I come across data sets that seem cherry-picked.
Yeah, that's a very good question, and I think it also applies here. So there's this chest Xray 14 has got a lot of criticism for labels being not fully correct, and a lot of the labels were also extracted automatically from, so they were taken from the PACS and not assigned upon second review of the images. So I think that's definitely one of the issues here as well.
Okay, thank you. Any other questions from Japan? Do the efficient net and the UNet share some of weights? Since I saw there were some lines connecting the two nets.
The UNet is based on the output of the convolutional layers in the efficient net. So it doesn't share the weights, but it does get, it uses the layer outputs of, I think we made 4 connections there. So at different scales, there's a connection going into UNet.
Okay, and final question, do you have an idea of the inter-observer variability for manual annotations?
Yeah, that's a good question. Actually, yeah, unfortunately, we didn't have the manpower to do that, because that would, yeah, really, you would have to annotate the same images twice by different observers. We were quite happy that we got the full data set annotated by, you know, any observer in the first place. So we don't know, we don't have numbers on that, unfortunately.
Okay, thank you. Thank you again, Ludo, for the presentation. We move on to the next part of the program, which is the break. So you can go back to the lobby, or you will be sent there, and there you can go to the networking part, where you can go into the networking carousel to talk to some people that are also online, and we'll be back with presentation of Japan Go at 2:30. So I will see you all back in the lobby.